Hello, guys. Hello to everyone. My name is Gilberto Thomas. I am from the University in Porto Alegre, Brazil, and I have been collaborating with Professor Glazer and his group for the last 20 or more years. Just remind you about this lecture. It is being live streamed at YouTube, and it will be recorded also and distributed later. Okay. What I'm talking about today is a continuation of the lectures before from Julius, continuing with the cell property and behavior. Specifically, we are going to talk now about cell growth and cell division. Okay? Well, the outline of the lecture will be this one. I will introduce some few motivation from biology to include the cell division, cell proliferating in CompuCell, and then we are going to implement these properties, these behaviors in the CompuCell. So we are going to do 3 examples. I will write the examples on the screen, and you can follow either by downloading from the repository of the demos in the student materials, or you can just watch and do the exercise later. Okay, so we are going to implement the cell growth, then we are going to implement cell division, and then we will use some mechanism to regulate both behaviors in the cells. I mean, we are going to use the pressure on the cells to control the cell growth and consequently the cell division. Okay, let's go on. Oops. Okay, if you want to have a multicellular organism, you have to have your cells proliferating and survive, differentiate, or die. I mean, there is a bunch of cell behaviors that you have to take into account to simulate, let's say, multicellular organism. To each one of these stages of the cell life, some decisions have to be made about what kind of factors can determine or influence the cell division, cell growth. For example, if you have the cell has disposal growth factors in the middle where they are, these growth factors can promote cell proliferation. On the other hand, if you have too many cells in contact with each other, this contact between them can inhibit the proliferation. So there is a grand variety of factors that influence, that promote, or one or more of these behaviors on the cell life. Basically, when a cell decides to proliferate, they must enter in a cell cycle. The cell cycle is composed by 4 stages, each one full of mechanisms that prepare the cell for the division, which is its goal at the end. Okay, we have those 4 phases here, which are the phases of the cell cycle, and each one of these phases is characterized by a very specific behavior inside the cell. The nucleus have to be destroyed, the DNA has to be elongated and pulled to the side of the cell has to divide, it has to separate the chromosomes, and finally the division occurs. So at each one of these phases, they have a lots of mechanisms that they are marked for checkpoints. Okay, when the cell goes on a specific stage of the cycle and prepares itself to advance to the next phase, it faces a checkpoint that the cell has to check. For example, from going to phase S to phase G2, or going to phase G2 to phase M, there are some checkpoints that we have to take into account. The question is, how do we implement this kind of mechanism in the cell? Of course, this is a very complicated mechanism. We are not going to model subcellular systems yet. That means we want to model the entire cell cycle for now. But anyway, we have to take into account what can affect the growth rate of the cells. I mean, how fast or slow the cells grow. For example, if the cell has available space, if the cells have enough nutrient to take up, how fast they can convert the nutrients into mass, if this conversion is efficient or not, if they have growth factors in the environment around the cells, if there are contact between the cells, and which is the state of the cell, if there are toxins in the environment. So it's a lot of things that the cell has. We have to decide at the beginning to model the cell division and proliferate. See, here is a small move here. You can see the stage, the cell grows, the nucleus is destroyed, the cells are, the chromosomes are pulled back to which side, from one side of the cell, and then the cell divides, okay? Anyway, but to begin, we have to start with very simple rules to make our cell grow before divide. Okay, the easiest way to do this in CompuCell, to implement cell growth in CompuCell, is to make the cell target the increase in a constant amount. For example, at some time interval, some number of Monte Carlo steps. So we replace the target volume for a expression that sums at each interval of time certain amount of target volume. And when you have to decide this which is the size of the cell the cell has to have to divide, will promote the division. So this is the plugin here where you have to define the behavior of the cell target. At the beginning, like we did in the simulations from Julius today, you declare the cell target volume and the lambda volume as fixed values at the beginning, at the start function of the steppable of your simulation file. And in the step file part of that steppable, you make the increasing of the cell target volume at some time interval, some number of Monte Carlo steps. Okay. Once this is done, let's practice a small exercise here. It's a long test because it's a test that I will do here, showing to you. Let me divide my screen here to show to edit. You can open to edit now. I will go slowly, and in this simulation, I will assemble the use the wizard to build the simulation. And as the simulation is ready, I will go over the steppables and analyze each part of it to say what is the function of each steppable, of each part of that step. Okay, let's start the simulation. Go to project, new project, say something like the name of the simulation, E231, exercise module 2.3, exercise 1. And I am saving the simulation in a specific folder in my desktop that I call the -temp. So go on. So we have to build a LETS with 100 by 100 points, and by once it means that a 2D grid, 100, 100, 1. And the boundary conditions, well, our cells aren't going anywhere, so we don't mind if they are confined in a box. So we are using no flux boundary conditions. It means that the cell cannot cross over the boundaries and appears elsewhere. We are going to use here the blob initializer. Okay. Go on, and we are going to create a cell type that I will call simply cell. Only one cell. Okay. We are not going to use any fields. Go on, and here I will add the usual contact energy, the growth steppable, which is here. When you use growth steppable, see, I will unmark. Look at this simulation wizard page. We have two options to choose which plugin we are going to use on surface and volume. Volume flex and surface flex allows you to define these quantities like cell volume and cell targets in the XML file. If I choose the growth, I don't have those options. The only options available are volume local flex and surface local flex, which are defined the values for the targets and lambdas in the steppable file. I'm going to show you how, okay? So let's choose volume local flex and surface local flex. This plugin, the way it's written, it allows you to if you put your cursor over well, it's not showing anyway. It's here. It allows you to define the quantities, the attributes for the cell, like volume and target volumes and lambda volume for each cell. The other way, when you define in the steppable, you define for each type of cell. Okay, this is for personal information for each cell here. And we are going to use the center of mass. We don't need cell neighbors right now. So go, and you have your simulation finished. Here it is. I will open here. Here is the structure of the files. The XML. First, let's fix the XML. We need a single cell center in the middle, put in the middle of the lattice. So I will use a radius 5 cell with also 5, okay? And for the XML file, this is what you have to change, just this number, to adjust the size of the cell. Now we will go to the step. here is the structure of the step. The first line is some machinery to import the executable of the extrapolable from CompuCell core. Okay. The second line import a mathematical library from Python if you want to use inside this steppables from this file. Probably we are not going to use in this steppable right now, but it comes as a default in the steppable .py file. So the constraint initialized steppable is the one which is included in this file when you choose the volume local flex plugin. See, I'm going back to the XML file. Here is this volume plugin with nothing to be included here, just the call for the plugin. This call here makes the steppable include this class, this constraint initializer steppable. And here we are going to say that each cell in our simulation has cell target volume 25 and cell target volume 3, as I propose in the exercise. So you change it here. So this is defining the start function of the steppable. The steppable start function is a function that runs only once. See, there is no attribute here in the function saying in which Monte Carlo step this function should be called. It's only once at the beginning, at Monte Carlo 0. Okay, to define the attributes of the cell. If you have more things to define from the beginning of the simulation, here is the space where you should include it. Okay. Now, the next step to fix the simulation is to change the growth steppable. See, when there in the wizard, when they included the growth steppable, this is the part of the steppable, the class, which is included here in this file. We have the growth steppable. There is a initiation part here, which is default from the code. And it has no at the big start function, because if you want the cell to grow, it will grow in the step function, because the step function is called at each Monte Carlo step, or each how many Monte Carlo steps you want. Okay, so in this Monte Carlo, in this part here, I will say that our cell will grow at the rate defined in the problem here. See, 25 voxels per 500 Monte Carlo steps. So I change this number here to 25 point, because it's a real number, divided by 100. Sure? Okay, so this is the implementation of the growth rate. We are now want to learn another feature from CompuCell, how to plot graphs. Probably next week there will be more. Oh yes, I forgot to type the wrong number. Thank you. 500 Monte Carlo steps. That means that each 500 Monte Carlo steps, the cell doubles its size. Okay, so we are plotting graphs. How do you plot a graph? How can you see the evolution of the cell volume with Monte Carlo steps? Okay, I will tell you how to do that. Probably next few lectures we'll have more activities on plotting graphs. But let me show today. So here, to plot a graph, we have to create a new window in the player where the graphs will be plotted. So where will do that? Well, if you are going to show here as the exercise proposed the volume of the cell with Monte Carlo step passing, so we have to include this graph in this class, in this step. To include the graph, the graph window, it must, as I told you before, always you have to include one thing for the first time. This thing must be included in the start function of the steppable. Well, here in the growth steppable, we don't have this start function because the cell starts growing at the first Monte Carlo step. So the 0 Monte Carlo step, there is no growth, only the second one. So we have to create here this start function. So I will include here that start self. Like I did, like the other steppable there. So I created this line, started self, and here at the started space part, I will include the graph. How? Okay, you go to cell CC3D Python drop-down menu, and here there is a tab called Scientific Plots. In this tab, you have many options. The number one is the setup of the window, of the plot window. See, there is a parenthesis say that this is the one you have to put in the start function of your steppable. So you click here, you have the graph window being created in the start function. This graph window is composed by some instructions. For example, you have the title of the graph window. For now, let's say we want to plot cell volume. Oops. And we can title the axis. The x-axis is Monte Carlo step, is the time of our simulation. And the x-axis, we have the volume of the cell. We also have the option to make the graph present grids or not. I will let this as a false to begin, and then I will change to true to see what happens with the simulation. Okay. I don't have the CC3D Python menu here. Where? In NanoHub? Wow. What's going on with that? Okay, let's try to do something else. I don't know if you can copy from the folder, the demos folder. You can download the simulation from there and upload it to NanoHub maybe, and you have this code completed to follow it, for example. Okay, let's see who. Okay, let's go on. Okay, try to download from the students the students' material and upload to that. Yeah. Yes, you can do that, but I don't know if you can copy from the meeting chat to NanoHub window. Anyway, let me go on. So, look, another thing that is interesting here is that in a single graph window, you can plot as many as curves as you like. The only thing you have to do is to define like a placeholder for a chosen curve. So this line 29 and 30 here are creating a possibility to plot two lines, two curves, two simultaneous graphs in the same plot window that I have created. Okay, so we have then created here by default from the drop-down menu two windows. One that is called vol, another that's called surf. We are not going to use this surf right now, so I will comment it. Okay, so now we have our plot window created. How to implement the graph? How to plot the thing you want in that window? Now this is made in the step function, because here is where we are updating the volume of the cell. Actually, we are updating the target volume of the cell, and the simulation updates the volume according to the target volume. Okay? So I will include here a line from the drop-down menu again, scientific plots. See, there is here, add data points. It's a line that must be included, see, between parentheses in the step function. So I click at that. By default, it comes with the two lines because I have created it at the beginning. I had created two graphical possibilities to be plotted there. So I will comment the second one again, because I don't just want to plot one thing now. And this one thing that I'm going to plot is in that I have to refer here in this line the window where I'm going to plot this particular evolution, the volume evolution. So I call this plot window here as mvol, then Ceph add data point at window mvol, and then x data and y data. This is what this commented line here is telling you. Arguments are name of the data series, mvol, x and y. Okay, x is the MSS, which enters into steppable through the function, and y is the cell volume that is an attribute from the cell, for the cell. Okay, save the code, and let's see how does it look like. Go here, open in player. Where is the player? The player is here. You can come here and tile the simulation, and you have both things simultaneously on the screen. The cell growing here slowly, because it's growing at each doubling its size at each 500 Monte Carlo step. And here you can see the increasing of the cell volume according with the simulation running. Okay? This is a very handy thing to use in CompuCell, graphs. Okay, let me stop here a little bit. So I will change something there, which is the, oops, what is it called? Here, changing the graphic window. I said to you that I will not here. Where my code? It's closed. Oh. Okay, it's here. Here, I will change it from false to true here. Okay, and if you run the simulation now, you can see the appearance of some lines that I don't know where my simulation went, but anyway, so I will comment this line here and here and here, because this is the old simulation. Let's see if it works. Save it. Oops, sorry. I think it's going to work better in your code than mine, because mine is kind of mess right now. I will restart from the beginning. It's very easy. Right. Let's see if we have the simulation here. Here. Okay. Now I have it. Okay, here now I go to from true to from false to true. Save and open and play, which is here. See, now you have the grid. You can track more easily the quantities with the help of the grid. Okay. So now I will stop and continue the simulation. Now we can add another window in the same graph, another data series. So in this data series, I will track the values of the, I will do a simple thing. Let's see the influence of the cell surface constraint in the simulation. I will add here from Python again, cell attributes like lambda surface and cell, where is it? Target surface for the cell. Okay, and I'm going to say that the lambda surface is also 3, and the target volume is 20. Target surface pair, sorry. I'm saying that this is the cell target surface is written this way. I think I got the wrong drop down. So this is right now. So look, we are saying that the target volume is 20 and the volume is 25. And our cell starts with a cell of radius 5. Okay, let's see what happens when we do that. But let's do also to keep track of this the plot window, including now the tracking for the cell surface. Of course, here we have to change title and surface, for example. And okay, here, let's put variables to be consistent. Save it, go, open in player. Where is that? See here, tools, time. The red one is the volume. The green one is the surface. See, the way it has been plotting is the way it was included by default from the wizard, from the to edit drop-down menu. But we can improve this visualization by change here. See, we can, the plot may be put in the graph as lines or as dots. Right now, that the window I showed you, we are plotting dots with color green of size 1. So it's better to change this to lines, then it's going to be a more visible change. And here I will put 5. Saved, go. So I have to go every time in the window. Now we have here the cell growing as a square. Why? Look at your code and tell me why the cell is going like a square. No one? This is the effect of the constraint in the surface. Okay, see the surface is fixed in 20. Okay, so although you have this increasing in the target volume, which makes the volume to increase, the target surface is kept constant. So the cell is compressed in a way that he can adapt his shape according to the energies, the contact energies we have defined at the beginning. So we have to change this thing to allow the cell acquire the right shape during the evolution of the system. How do you do that? For example, in the third step here in the exercise, we are going to do that. Let's assume that the cell is a circle, because we are in a 2D simulation, okay? And the surface, which is going to be the perimeter of the circle, will adapt according with the radius, the volumes of the cell. How do we do that? Here, since we are going to talk about, circles and perimeter of a circle, we need a very old known constant, pi. Let's define pi here. We could use pi from the numerical library, but let's define here because it's faster. And the numerical library will be treated later. So pi is 3.141569, blah, 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 so on. That number is good enough. And here we are going to say that the cell dot target surface will be equal to 2 times pi times square root of cell dot volume, just like that. Yes, I thought, as I thought, NP.pi would work as well. But for now, let's use this way because I'm not calling the library. It's another thing to explain later. So and now save it. Doesn't matter the when you change, because this will use the volume of the Monte Carlo step, the previous Monte Carlo step. There is no there is no way. We can update later, but as we are updated according to the volume, not with the target volume, it doesn't matter. Okay. So let's see if how it goes. There. See, now the cell is round again. Okay, thanks, Pedro. See, both are growing. The green line is for the surface or perimeter of the cell, and the red one is for the surface of the cell. And the perimeter goes with the square root of the surface, and the cell is round again. Okay, so in this simple example, I showed you how to regulate the cell shape with the surface plugin, and how to plot windows, to plot graphs for the behaviors or anything related to the simulation. You can plot in a window like that. Okay. Okay, let's go. Let's advance. Now, everything that I told you, it's in the presentation, which is available to you, and you can follow step by step later, okay? So we don't need to go this slide right now. Now we are going to think about cell division. So on the cell just, I don't know, it's quite popped up here, it's this thing. I have no idea, anyway. But for to have that multicellular organisms, you want the cell have to divide. So the question is, what triggers the cell division? Well, we saw in that steps that the cell suffers lots of transformations till to reach the point of division. But we have to decide a simple thing right now, because it's to simulate the all cell cycle phases is a big, ambitious simulation. So here, this is a small movie that I don't know why it is popped up here, and I cannot move it from the center of the screen. You can look here that there is only one cell being undergoing mitosis here, this one, and there is a slow process and very complicated one. But for now, let's choose our trigger condition will be divide the cell when it doubles its volume. For example, it's a choice. We can choose anything. So let's do the talk about CC3D cell division. So to divide the cell, we start with one cell, like I did just in that example, and after division we have two cells. So we need to create a new cell. Let's call for now that the parent cell is this beginner cell, and daughter cells are the ones that results from the division. Okay, so we have a lot of decisions to make to implement the division. Among them, we have, for example, which parts of the parent cell goes to the daughter cell, to each one of the daughter cells. What is the plane of division? Like you see in this picture here, you can divide that along the major axis of the cell, along the one axis perpendicular to it, or in a random orientation of the cell. Another question, are the cells have the same size? We don't know. What are the attributes that the parent cell, the cells inherit from the parent? The target volume, target surface, so many other things you can attribute the cell, like state, something like that. Are the divided cells, the daughter cells, of the same time or are different? And after the division, the parent cell stays in the same state that it was before, or in another state. And in which state the daughter cell will appear, in the same as the parent or in another completely different state. So we have many possibilities to take into account if you are planning to do a simulation of any biological process. Okay, for now we have available from CompuCell a specific steppable called Mitosis steppable. It has two basic structures. One, which allows you to perform the division itself, considering what happened with the cell during the simulation. Okay, and in this part we have to say, okay, these properties, the cell properties that the daughters will have, and the values of these properties must be typed by hand. So we decide how the daughter cells has to be. Okay, what triggers the cell division must be included in this steppable. So we iterate over all the cells in our simulation and see if the cell reached that trigger point, put it then in a list, and in a list to divide. For these cells are ready to be divided. Okay, and then we go to the mitosis step, we divide it. Okay, this is how it works. So I will explain now, building a small simulation here, which includes this steppable. So bottom line, we have first a parent cell. It's a unique object in CompuCell. And after the division, we have two daughter cells. But for sake of being practical in CompuCell, we are saying that after division, we have the parent cell remains, and we have one child cell. This is easy to make the the transference of attributes to clone one cell, a daughter cell from the parent cell, for example. So we'll keep the name of the original cell and name the new one as child cell. It's just for coding convenience. Okay, let's do the exercise now with the mitosis. This is the exercise. Again, you can take it from the student's materials and to upload to NanoHub if you want. Let's start a new project here. New project that I will call E232. Next. And I will have 2 cell types in a grid of 100 square grid points. Again, with no flux boundary conditions. And I will start with a blob initializer. So the cell types would be ST for stem cells, and TD, thermally differentiated cells, which is going to be one of the child cell. Next, no fields, contact, growth, and now we have to include the mitosis step. And again, volume local flex. We don't need now the surface local flex plugin, but we do need the center of mass. And next, finished. I will close the first one. Keep on the side. Here, let me go over the steppable function. Mitosis steppable to show the structure of it. James has showed something 2 days ago in that cancer simulation demo he made in his lectures. But here it is. We have the first function, the step function, where we create a list of the cells which are going to be divided. So cells to divide is an empty list. And then we run over the cell list and see if the cell satisfies the trigger event, which is going to be the double of the size now. For example, here. See, the cell, I didn't change yet, but see, the cell is radius 5, and this initial target volume is 25. So if the cell volume is 50, it means that the cell has double its volume, and then here is the trigger. If the cell has the volume bigger than 50, so append to the list. So the cell is ready to be divided. Okay, this is listing the cells. So if now I'm going to again to a loop, but in the list the cells to divide. I'm going to divide the cells in the second block here in line 49. So for cells in cells to divide, and here there is a possibility, 3 possibilities, for example. Cell dividing in a random orientations. The copy cell randomly pick axis in the cell object and divide it according to that axis, half and half, for example. We can say, okay, choose a specific vector-based orientation to divide, or to divide along a major axis or along the minor axis. This one has to be to work with another plugin in the simulation wizard, which is the inertia moment of the cell. we are not going to use this one here. No, we are randomly divide the cell. So the second step is, okay, now we have two cells being divided. We have two cells here. What do we do with those cells? At this point, we have the parent and the child cell. And then we have to pass to the cells the attributes they must have. So I'm saying that the parent cell, which has been divided, has the target volume, which was 50, remember here, divided by 2. And we are saying that the child cell will be exactly equal to the parent cell. This is command here, clone, parent to child. So the child cell is exactly equal to parent one in attributes. Okay, they have a different type, but the same attributes. Okay, here we are attributed the type of the dividing cells. For example, I'm saying that if the parent cell was the type 1, I mean, it was stem cell, ST cell, then the child will be different, would be a TD cell. Else, if the parent cell is a TD cell, the child will be a ST cell. So we are making everything symmetrical. I mean, every time a cell divides, it creates one of each type of cells. Okay, you understand? Gotcha? So, now I have to come back to the XML file and create the single ST cell in the center of the grid. So, with the radial size, and say that they have cell target 25 and volume lambda volume equals to 5, and again implement the growth 25 over 500. Now you are ready. Okay, let's see how does it work. Open in player. Here it is. See, the cells start to divide, and each time they divide, they create one of each cell. We could accelerate this process by saying that division occurs if a cell volume is bigger than 30. Let me put back the XML file here. Somebody is asking for that. In the XML file, I just created the cell in the center of the blob 5, and they create only one ST cell. Because when you include the blob initializer, by default, it puts in the types as many types you created here in the tag types. So I erased the TD and left only the ST type that. See, we can accelerate the simulation here. If you go to the steppable file and the trigger event, I say that the volume is bigger than 30. For example, the cell grows faster. I don't know if it's very perceivable. Yes, I think it is. Then you have all things grow exponentially. Now we can see change a little bit the rules for division. Here we are checking to see if every cell has volume above 30. But I'm saying that I want to divide only the ST cells and not divide the other ones. So how do you do that? Well, we have to change the rule. We change the rule, changing the list of the cells we are going to include in cells to divide the list. And here, let's visit only the cell type here. I'm gonna get rid of this comment here. And I will say that the cell which is going to be divided is cell S type SCT. And comment this line. Let me get rid of this. Okay. Okay, now I'm with this line new line 46. I'm saying that I will check only for the size of the stem cell to see if it is ready to be divided. If it is ready, I append to the division list. And then I divide it according with the same rules here. Okay? Save it. See, now I will remain with only one stem cells, ST cells, and many others TD cells. And the TD cells are not divided, although their volumes are growing, because I didn't put any restriction, any constraint on the volume of the green cells. Okay, so this small example gives you how the mitosis steppable can be used in a simulation. Let's go back to the presentation. Okay, if I let that simulation grow forever, it will fill all the space available. At some point, the number of the cells will, when this is the case, the space will be filled, the cells cannot grow anymore. If the cells doesn't grow anymore and the target volume remains increasing, the cells, we say that the cells will be under pressure because they want to grow, but they cannot grow because they have no space to do that. Okay, how this pressure can be calculated? Well, from physics, a little bit of physics now, I think it's very easy. But anyway, in physics, if you have the energy of the potential energy of a system changing in the space, then you have a force acted over this system. Okay, so the energy is increasing with time because the target volume is increasing with time. So if we have all the time this force acting in the cell, this force can be interpreted seen by create a pressure of the cells, which is a force over the perpendicular area available to it. So if you use the definition before here, this definition, in the second equation, substitute F by dE over dx, we will have this final expression that A times area times x, it's a volume. So pressure is a variation of the energy over the volume occupied by the cell. Okay? Now, we know that in our model, our composite cell model, the volume energy is calculated this way. The Hamiltonian, the Lagrange, the Hamiltonian from the energy is this one. It's a lambda volume times actual volume minus target volume square. So if you are analyze how does it change according to with the volume variation, we have this. This is a derivative of this expression on the volume term variable, what gives you this expression in red here. So pressure is written in CompuCell, in our model, as 2 times lambda volume times volume target minus actual volume. This is a takeaway. You can learn this if you want in the first discussion, okay? But for now, it's what we do. What we do need to know is how to write pressure in CompuCell. It's 2 times lambda volume times volume target minus actual volume of the cell. Okay, let's move on. Let's use pressure to control cell growth then. How do you do that? Well, here in our simulation, the pressure will be exerted by the neighbors. I mean, the contact between cells. Okay, so we have to change that constant growth, the G factor, which was in our previous examples 25 over 500, the growth rate, by a function of the pressure, like this. F is a function of the pressure of the cell. This function can be anything, reasonable thing, actually. For example, we can have in these 3 different proposals here, linear variation of the pressure in related with pressure of reference. We can have exponential. This is a Hill function. No, I don't remember the name of the function. It's I think it's a Hill function of the pressure with pressure of reference as a guide, or a Michaelis-Menten function like that. It's a sigmoid function like that. We can choose any one of those, which ones is more favorable to reproduce your experimental results you might have. You choose. Now, how do we implement that in the simulation? Let's do that, okay? So I'm going to close this one and get to the one, new project, E233, same directory. same. See, which is written in small letters there, is to create a simulation that is quite similar to the previous one. With two kinds of cells, ST, ED. Next. I'm going fast at this part because this part is, you already know. Contact, growth, mitosis, volume, the only center of mass. Next, finish. Okay. Expand. So let's start adjusting the cell at the center of the grid. 5, 5. Only the stem cells. And here the values stays like they are. I think here is 5, according with the last one. The growth is 500 over, no, 25 over 500. And what else? Every cell divided to double side. I will not change this one. Okay. So now we want to keep track of the target volume of the cells. I mean, the average target volume. This is a little bit more complicated example because I'm going to, as we have many cells, instead to plot the cell volume, we will calculate the average of target volumes of the cells and plot the average value. Okay, so let's do this. I have here maybe it's the first step is to add here in the gross steppable a window to plot the values we want. So def start self and scientific plot setup. Okay, average volume. Average target volume. Time, I will call here AVTGB, and I will call the data series AVT. I will get rid of this window here. Okay. Now I have to plot the target volume. But to plot the target volume, I have to calculate the average. I have to calculate the average. So how do I do that? I would create here in the step function a variable like AVT, TV, target volume, equals to 0. Okay? And I will run over the cells. And before I update the target volume, I will sum here the actual target volume. I mean, at this point, this variable here is accumulated the values of this target volumes of all cells. Okay. when the loop ends, I have to calculate the average value. How do I calculate the average? Well, I have to measure how many cells I have in my list. So I will divide the accumulated value like this. Divide equals to len of self point cell list. Okay, len is a Python command that you remember from Bob's class on Monday, which gives you how many elements the cell list has. So when I divide the accumulated value or the length of by the number of elements of the list, I'm taking the average of that value. And this is the value now that I'm going to plot. So go to Python, scientific, the data plot. So I'm plotting the data series that I call AVT, MSSL, and AVTV. I don't need the other window. Comment. Okay, so this is the way I'm calculate the average target volume right now. Save it. So open in player. And here you have both windows. Sometimes this cell window doesn't appear when we reshape the player. So what's in the graph window, you are seeing the cells increasing the average target volume till it reaches the size of 50. Then division, the mitosis occurs, and the target volume goes down to 20 something, the middle. Then start to grow again and divide, grow again and divide, and so on. Okay, this is what how do we keep track of this average value? Okay. Now you know how the cells change the average volume of target volume. So what about pressure? How do you calculate pressure now? Okay, now we have now to create a dictionary for the cell to keep track of the cell pressure. So here I will define the dictionary. The dictionary attributes a cell a new attribute. This way. I think you learned that in Bob's class as well. Cell dict. I will call this attribute as pressure, and I will initialize it as 0. Okay. So now I can to calculate the average pressure of the cells, and to see it in a graph, I will create here a graph called AP, for example. AP, average pressure, lines. Now, I think it's better than to, now it's a question. I think now, because, you know, the values of these quantities are much different, it is better to create a new plot window to show both results in a different window, each one in its own window. So it is better to create a new one here. I will create a new plot window here, this way. Go again to the scientific plot, start function, create a new window. But now I had to name it differently. I will call this Win2. It must be different this one, because this window was already created this part, and I will create a new one here. It has to have a different name. So here I will write average pressure, Monte Carlo step, the window is, I think it's out of alignment. AP lines, green size 5. So in this window, I'm going to create a plot for the average pressure. And now I have to measure this average pressure. Okay? And how do I do that? I have to say that the pressure is here. Running over the cells here. Cell dictate pressure, it's equal to 2 times cell dot lambda volume times cell dot target volume minus cell dot volume. Okay, this is the expression I showed before in that physics part of the last slide, the previous slide. Okay, so 2 times cell lambda volume times cell target volume minus. So I'm saying that this cell here, which is in the list, is under the pressure calculated by this way. And to calculate the average, I will define again a new variable, average pressure, and I will increment here, accumulate here, AVP minus equal cell dot dict pressure. So I'm accumulating all the cell pressures in this variable here. And again, I have to average it. AV, I will duplicate this line and say AVP is this. And I will plot now the pressure in the second graph window. that I call AP and plot AVP. Okay, save it. And let's see if I didn't make any mistype. I think I did. Let's see. What is the error? No, not this. I have to search for the error window here.
Your pressure calculation, lambda, you have a typo.
Excuse me?
You have a typo on your pressure calculation with lambda.
Ah. Oh, yes, here. Thank you. Let's see. I hope it's another error. That happened. An indent. Misindentation. Let me see the indentation better this way. Here. Oh, come on. Now we have. Let's tile it. I don't know why it's not showing here, but okay. Both windows have been created. The other one is working, so the problem is with the new one. Let's see what is the problem here. Plot AP lines green size. AP. What's going on? There is no error. This is the worst thing you can have in a simulation. An error that is not showed. Why is not showing? Let me try something to see if you, let's do a checkpoint here. Print AVT. Just to see if the thing is being calculated correctly. This should appear. No. No. Strange.
Line 39.
30.
To
Here. Here. Thank you. Yes. So let's get rid of this. Save it. The simulation was working, so we have to. Now it's crashing. Okay, come back. Well, when you do this alive, that can happen. Okay, finally. So you have the target volume, you have the pressure. The pressure is mostly constant here because the cell is not dividing yet. Let me accelerate this simulation a little bit to see the effects more fast. Let's do the following. Let's just double the time at 100 Monte Carlo steps. Okay. See, these cells are doubling. I'll let the cells fill the space to see the effect, see what happens with the pressure. The pressure is increasing because the cells are becoming confined. Now they are not dividing anymore, but as the target volume is still increasing, the pressure is still increasing. This goes to infinite if you allow it. So let's control that. How do you control that? Let me go here. Here, we have to control these things doing that. We have to modify the growth rate according with this rule, this function. Okay, let's do the thought. So where is the growth rule? The growth rule is in the growth steppable. It's here. Instead 25 over 100, let's multiply this. For example, now we have to define some pressure of reference, we will call P under half equals to something, maybe 35, something like that. It's a number. Then you adjust this number according to your needs, and here you put times max of 0 and this expression P half minus, this line must be after that. Oh, don't find, whatever. Maybe not. PF minus cell duct eject pressure. Okay.
Gilberto, I just want to break in here for a minute. We're a little bit over time.
Yes, just to finish this one, 2 minutes. Okay.
Sure. Yeah, we can try to finish up by 4:30.
Okay. See this line. What does line do? He is adjust the graph rule according with this rule. Why max between 0 and this difference? Because we don't want the cell shrink. So if by chance cell duct pressure is smaller than the P of reference, the cell target volume will not increase nothing. Will increase nothing. It will only increase if this number here, this difference, is positive. If it is positive, it's bigger than 0. So the max between a positive and 0 is the positive number. If the number is negative, the maximum is 0, and doesn't increase the target volume. Okay, so the cell will not decrease the size. It will be always growing or not, but never shrinking. Okay. Let me show this. I think this is enough. Let me see if how it goes in the simulation, in the layer. See now? The cells have reached the space, they filled the space, but the target volume reaches a plateau. And the growth and the average pressure is not growing too much. If you wait a little more time, this line will be reach also a plateau. So you can control the pressure of that system implementing this kind of control in the growth rate. So those exercises are available for you in parts. I mean, each 1, 2, 3 parts is separated in one specific simulation in a zip file in the demos folder. You can download it and do it for yourself, by yourself. Okay. So to end is just a final thing here. Everything is written here. So if you wanted to try another thing, you can implement those 2 different functions to control the pressure and see what kind of plateau the average pressure reaches. And that's it. Thank you very much. Please don't forget to answer the questionnaire.